In this video, we're going to look at how we can use quadratic functions to model real-life situations. One common use for quadratic functions is to model the flight of a flying object, anything that goes through the air. And at least in theory, that it should always be a quadratic. When you throw something in the air, its height should follow a quadratic function if we ignore things like air resistance. Okay, so there's an example here with the height after so many seconds, after t seconds being equal to this. So that means that, for example, after 2 seconds, it would be the height would be 15 times 2 minus 5 times 2 squared, whatever that might be. Okay, so the height is a function of t. The height depends on t. So the question that's asked here is, what is the maximum height of the ball? Now the height's this is what happens to the ball. It starts low and goes up to the top and goes down again. So we're interested in this point here. So if this graph is a graph of this function, the 15 minus 5t squared, we should be able to find the vertex. And the height of the vertex should be, or the y-coordinate of the vertex should be the maximum height. So what we need to do is to find the x-coordinate of the vertex and then substitute that into this expression to get the y-coordinate of the vertex. So first thing we have to do, we need to find the x-coordinate of this thing. Now we've written t equals negative b over 2a, but that's really t is just playing the role of x. So if we do the calculation, we can just be quite careful about what our a and our b are here. Our a is the number multiplying the t squared, just like a was a number multiplying x squared. So our a is negative 5 and our b, the number multiplying the t, is 15. So we've got to take those numbers and plug them into this equation here. Okay, so we've got our a was equal to negative 5. We've got our b, it was 15. So when we calculate our t, it's going to be negative 15 over 2 times negative 5. So negative 15 over negative 10, giving us 1.5. So it's after 1.5 seconds. After 1.5 seconds, the ball reaches its maximum height. How do we find that height? Again, we take this 1.5 and we plug it into this equation to get the height. So the 1.5 gets plugged in here. The 1.5 gets plugged in here and here. If we do that, what we should get, taking 1.5 and putting it into that equation, is this, 15 times 1.5 minus 5 times 1.5 squared. If you do the calculation for that, it's 11.25. So the maximum height is at 11.25 meters. Now in part B, it asks how long is the ball in the air, for how long, how much time does it spend in the air before it hits the ground right here. Probably from looking at this, you can tell that the answer is going to be 3, because it's going to spend half the time getting to its maximum and half the time coming down. But let's just go through the motions. What we need to do to calculate that is we need to solve this thing here, the 15t minus 5t squared equal to 0, because at this point at the bottom, the height is going to be 0 again. So if we put the height equal to 0, so 0 equal to this expression here, that should be something that should give us the t that we need. So if we do that, solve this equation here, you can solve it by factorizing. So if we factorize 15t minus 5t squared, we get 5t times 3 minus t. And then you can either solve 5t equals to 0, which gives you t equal to 0, that's the start, or you could get t equal to 3. In example 2, in this situation we've got the Versoix River running along here, and somebody wants to build a rectangular enclosure next to the Versoix River. There's no need for a fence along here, but there's going to be a fence here, here and here. Okay, so our job is to try and find the maximum possible area for that enclosure. How to make this area in here as big as possible. Okay, so the length of this fence is going to be x plus y plus x. In other words, it's going to be 2x plus y, and that in the question it tells us that that must be 100 meters. In the question it says there's 100 meters, so the 2x plus the y has to be equal to 100. That's our equation here. Now, it would be possible to rearrange that. Right? We can rearrange that equation so that y is equal to 100 minus 2x. So if we wanted to find the area now, this y we can think of as being 100 minus 2x. So the area in here is going to be x times 100 minus 2x. Okay, so if we do that, going from the start, it's x times y, but we know that our y is 100 minus 2x. And so we can get a nice expression for that, a nice quadratic expression for that. A quadratic expression that has a equal to -2 and b equal to 100. So if we want to know what value of x gives the maximum area, we can just use this formula. So we put -b, which is going to be -100. We divide it by 2 times a, which is going to be -4. So we're going to have -100 divided by -4, and that gives us 25. If we then take that value of x equal to 25, because that's not the area, right? That's the value of x that gives the maximum area. If we take that value of x and put it back into the expression for the area over here, or into this expression here, we'll get this, -2 times 25 squared plus 100 times 25, and that should give us 1,250. So the maximum area is 1,250 square meters. The second part of this question is actually easier. The dimensions of the enclosure. Okay, we know that x is going to be equal to 25. So this is 25, this is 25. If it all has to add up to 100, that means that y has to be equal to 50. If you want to do that more algebraically, we can do it like this. We can say that when x is equal to 25, y is equal to 100 minus 2 times 25, and that's equal to 50. So the enclosure is 25 meters by 50 meters.